Have you ever wondered how engineers design the massive pipeline networks that transport our energy or the intricate cooling channels that keep our computers from overheating? They can't just guess, they have to know exactly how much pressure is lost and how much pumping power is needed. That's where CFD or computational fluid dynamics comes in. It's like a virtual wind tunnel that lets us see the invisible flow of fluids. Today, we are going to build our very first simulation from a blank screen using OpenFOAM. But we're not just going to create pretty pictures, we're going to do what real engineers do, validate our results. We'll compare our simulation against a 100-year-old engineering formula to prove that it's accurate. Let's get started. To understand the formulas we're using today, we have to go back in time to the Industrial Revolution. Engineers were laying thousands of miles of pipes for steam, water, and oil. They faced a huge, expensive problem. They knew that the longer the pipe, the more pressure they would lose to friction. But they had no reliable way to calculate exactly how much. This wasn't just an academic puzzle, it was a $1 million problem. This is where our first hero comes in. In the mid 1800s, two engineers, a Frenchman named Henry Darcy and a German named Julius Weisbach, created what we now call the Darcy-Weisbach equation. Its genius isn't just that it works, it's how it simplifies the problem. It brilliantly separates the problem into three logical parts. First, the geometry. How long is the pipe and how wide is it? That's L by D. Simple. Second, the flow's energy. How dense is the fluid and how fast is it moving? This term, rho u squared over 2. This represents the kinetic energy of the flow. And third, the magic number F, the Darcy friction factor. This is the most important part. Darcy and Weisbach's insight was to pack all the complex, messy physics of friction, the fluid's stickiness, the turbulence, and the roughness of the pipe wall into this one single non-dimensional number. This was revolutionary. Instead of a different formula for every fluid and every pipe, we now had a universal framework. If you could just figure out the value of F for your specific situation, you could accurately predict the pressure loss for any simple pipe in the world. The Darcy-Weisbach equation became, and still is, the cornerstone of pipe flow analysis. But this created a new problem. The Darcy-Weisbach equation is useless unless you know F. For decades, the best way to find this F was to use this, the Moody diagram. It's a brilliant graphical tool based on the complex Colebrook-White equation, but it's slow. You need a ruler and you can't exactly put a graph into a spreadsheet or a computer program, not without jumping through hoops anyway. Engineers needed something faster for the modern age of calculators and computers. This brings us to our second hero. In 1983, Professor S.E. Halland, I hope I'm pronouncing that right, from Norway, developed this elegant formula. The Halland equation is a highly accurate, explicit approximation of much more complex the Colebrook-White equation. Explicit is the key word here. It means you can calculate F directly in one step. You just plug in the Reynolds number and you get your answer. The Halland equation is the power user's shortcut, so to speak. It gives us the accuracy of the complex underlying theory without the hassle of using a graph or solving a difficult equation iteratively. It's fast, it's efficient, and it's perfect for modern engineering work. For our video, it allows us to calculate our theoretical target value with precision and confidence. So, these two equations work together as a perfect team. Darcy-Weisbach sets up the fundamental problem, and Halland gives us efficient modern tool to find the missing piece of the puzzle. With both of them, we can now confidently calculate our theoretical pressure drop and put our CFD simulation to the test. Before we can trust our simulation, we need a target to aim for. The first step in any validation study is to do the hand calculations. For pipe flow, it all starts with one of the most famous numbers in the fluid dynamics, the Reynolds number. With water flowing at 0.5 meters per second in our 2 centimeter pipe, we get a Reynolds number of 10,000. This tells us flow is turbulent. Now, as discussed before, we use the Darcy-Weisbach to find the pressure drop. We have the length, diameter, density, velocity. Only thing we are missing is F, the Darcy friction factor. We can find F from a Moody chart, but a much faster way is to use an explicit formula like the Halland equation. Plugging in our Reynolds number, we get a friction factor of 0.0309. And now the moment of truth. Putting it all together, the theoretical pressure drop our simulation needs to match is somewhere around 386.25 pascals. Keep that number in your head. Let's see if OpenFOAM can actually find it. Before we dive into the complex world of CFD, let's start with something we've all done: drinking from a straw. We all think we suck the liquid up, right? But what if I told you that's not what's happening at all? What's really happening is that you're letting the atmosphere do all the work for you. Right now, the air around us is pushing down on everything with atmospheric pressure. It's pushing on you, it's pushing on the glass, it's pushing on the surface of the liquid, both inside and outside the straw. Everything is in balance. When you go take a sip, you expand your chest and lower the muscles in your mouth. This increases the volume inside your mouth. And according to basic physics, when volume goes up, pressure goes down. You are creating a small region of low pressure, a partial vacuum of sort. And this is where the magic happens. Suddenly, the system is out of balance. The atmospheric pressure pushing down on the liquid in glass is now greater than the pressure at the top of the straw. Nature always tries to balance things out. The higher atmospheric pressure on the surface of the drink has no choice but to push the liquid up the straw and into the low pressure area in your mouth. You're not pulling the liquid, rather the atmosphere is pushing it for you. This difference in pressure from high to low is called a pressure gradient, and it's the fundamental principle that drives all pipe flow. So, how much pressure can an average person actually generate? When you take a casual sip, you create a pressure in your mouth that is about 2 to 7 kilopascals lower than the atmosphere around you. That's only a 2 to 7% drop in pressure. But that small difference is surprisingly powerful. A pressure drop of just 7 kilopascals is strong enough to lift a column of water about 70 centimeters or over 2 feet high. That's the maximum length of a straw you could theoretically drink from while standing up. This pressure drop is exactly what we need to calculate in engineering. In our straw, it's a few kilopascals. In industrial pipelines, stretching for miles, the pressure drop can be massive. This requires enormous pumps to overcome it. Calculating this pressure drop with precision is critical, and that is exactly what we are going to do today with OpenFOAM. So this is the case setup for our simple pipe. I'll go through the case files one by one and explain what these are. So in the 0 folder, as usual, we have our field variables which are useful in solving our simulation here. These are the essential initial conditions, boundary conditions that we're going to provide. Let's take a look at each of these. So first we have velocity. Notice the units, that is meters per second, and initialized at negative 0.5 in the x direction. You will understand why this is negative 0.5 in just a bit. The boundary field, this include etc, is useful when we are running cases in parallel. It helps, the divided sort of domains talk to each other about where the boundary starts, where it ends, etc. We have our inlet, we have an outlet, we have the walls. Inlet kept at fixed value, outlet kept at 0 gradient, and walls at no slip. Next we have pressure. Notice the dimensions again. This is meter square per second square. indicating that this is kinematic pressure, not static pressure. Kinematic pressure being static pressure divided by density. This is again useful because when we visualize our results, we will need to multiply that with the density of our fluid. We initialize it at 0, and essentially the inlet kept at 0 gradient, same as walls, and the outlet kept at a fixed value. The value 0 here essentially indicates atmospheric pressure for our instances, if you can visualize it, since the static pressure is for our instances equivalent to our gauge pressure. This is we are operating in atmosphere. Next we have omega. Omega essentially talks about the specific dissipation rate. This is useful for the model that we are using. We calculated the value for it, close to 39.9 or 40. Dimensions is per second or second inverse. The inlet, it is kept at the fixed value of 40, outlet kept at 0 gradient. Now the walls are kept at a boundary condition called omega wall function. This is a standard wall function for your omega, used for k omega and k omega SST turbulence models in your Reynolds averaging. It's an automated or sort of automatic blended wall function, where if your mesh is very fine, if your y plus goes less than 5, it will resolve the viscous sublayer directly. Whereas if mesh is coarser, your y plus is greater than 30, it applies a wall function based on the log law. This makes it, sort of robust. It's more sort of forgiving for imperfect meshes. At the same time, it's quite essential for your k omega SST model as well, because that model is designed to leverage this blending capability in itself. Now, next we have nu-T. Nu-T is essentially your turbulent kinematic viscosity. This is the property that we are trying to solve for. The units here, meter square per second, initialized at 0. So you will see at inlet and outlet, this is set as calculated, meaning that the value will be calculated using your inherent field variables. Whereas for wall, we have set it to a condition called the nu-Tk wall function. It's a high y plus wall function. Unlike the omega wall function, it's not a blended function. It is explicitly designed for meshes where first cell center is in the log region, which essentially means your y plus is somewhere between 30 and 300. It assumes the log law of the wall, especially if your mesh is very fine. If your y plus is less than 5, then this boundary condition should not be used. But for our case, since we want our y plus to be greater than 30, we have used this condition. Ultimately, we have the turbulent kinetic energy. We have the units here, meter square per second square, and the value we calculated previously. The inlet is kept at fixed value, outlet kept at 0 gradient. The walls here is set at a condition again here. It's called the KQR wall function. Essentially, these are useful in handling the value for your K. What this function is going to do is it sets a 0 gradient value for turbulent kinetic energy, where idea is for physical assumption in the near wall region, we want the production of turbulence and its dissipation in local equilibrium, so to speak. In a typical simulation, you just want one wall function in isolation. Now let's take a look at the constant folder. So inside the constant folder, you will see there is again a folder called geometry. And inside this geometry, we have a VTK file. This is line.vtk. Let's open it up. First, you will see you will not be able to notice anything. Maybe it's because my background is set to white and my edge color is also set to white here. So if I just change the color, you will be able to see the line. I just click on 3D to, visualize it properly. So this line object that I have has the units of -2 to +0. Sorry, rather -2 to 0. There's no positive there. So this represents the skeletal structure of the pipe object that we are trying to make for our mesh. Essentially, we will take a circle and extrude it along this line using block mesh as we did previously. This is useful for that particular purpose. Let's go back to it once we discuss the block mesh ticked file. Now in the constant folder, I have two different files here. This is momentum transport and physical properties. Momentum transport talks about the type of simulation that we are running, whether it is turbulent or laminar. For laminar, it would just say laminar. For turbulent, it could be RAS, DNS or LES. RAS being the Reynolds averaging. The model that we are using is the K omega SST with turbulence set to on, and we are also printing the coefficients. Next, we have the physical properties. This is how we are going to calculate for our viscosity. Now, physically speaking, in our pipe, there are not many changes that we can expect in a thermal sense of the way, wherein we don't expect the temperature of our fluid to change drastically. So the viscosity will not be affected by the flow that we are currently studying. So the viscosity model that we can use is simply the constant, meaning that constant value of viscosity will be used throughout the simulation for any calculations. I want you to notice again the viscosity we've used here. This is kinematic viscosity, or rather the dynamic viscosity divided by density. This can be seen through the units here, meter square per second. The value is set to 10 power minus 6. Now let's take a look at the system folder. So the system folder contains all of these files. Let's take a look at them one by one. So the first file that we have, this is the block mesh dict file. You can start from the beginning itself. So we have the scale set to 1, then we have the radius parameter that we have defined with radius 1, and we have set the value to 0.01. Since our particular case, the pipe essentially has the diameter 2 centimeters. We are giving the extremities x0, x1, s1, s2 and c1, c2. So x0, x1, this represents the length parameter, and the s and c, these represent the other two dimensions in the circumferential sense of our pipe. We have defined the geometry using searchable extruded circle using the line VTK that we have created, giving it the radius value of this parameter that we had defined previously. In the same manner, we are creating these vertices. If you want to have a deeper look into how we have done this, I've already created a video about it. You can go ahead and check there. The important thing to note here, we have given 25 and 25 number of divisions across the radial and the circumferential dimension, and we have given 200 divisions in the length direction. We will see what that looks like in just a bit. But also notice we have given mesh grading to be 40, and we will understand why we've done that in just a bit. Ultimately, we have created the edges as previously discussed, and the default patch given as walls with inlet and outlet defined right here. Next, we have the control dict file. You can see the application set to foam run, solver set to incompressible fluid. Essentially, since this is a steady state analysis, we are running 20,000 iterations. This is no longer 20,000 seconds. We are writing a solution for every 100 seconds because we don't want to miss out on how the solution is sort of faring up, and also because we want to view what our y plus value looks like. The purge write is going to remove the latest time step for every 3 times your solution has been written. Since this is steady state, you're not really bothered with how your solution is advancing every 100 seconds, but instead you are interested in how the solution looks towards the end. Next, we have the decompose part dict. We are giving 4 subdivisions with a very simple hierarchical decomposer with the hierarchical coefficients present there as well. And I have defined a certain function called y plus. So y plus essentially talks about writing the value of the turbulent y plus. This helps in explaining the behavior of my fluid. This helps in explaining to my omega wall function where exactly is my first cell layer, and whether or not to use the viscous sublayer or to go ahead with the wall function route for calculating my turbulence. Ultimately, we have the FV schemes and the FV solution. With FV schemes, these are pretty standard. We have the steady state for the DDT, and for the most part, we have either Gauss linear or the bounded Gauss. In certain cases, especially with velocity, since we expect very transitional changes near wall, we have used the limited function here. And similarly for the flux, we have also used the linear upwind, but for the most part this is pretty standard. And ultimately we have the FV solution. This is where you define the behavior of your matrices, how exactly it is gonna be more diagonal, etc, etc. Again, these are pretty standard. For pressure, we have the GAMG. This is pretty effective. For velocity and the turbulence parameters, we've used the smooth solver because we don't expect them to change, or the gradients are not going to be as high as we would want, because if pressure is taken care of, then velocity and ultimately the turbulence parameters are going to be calculated pretty easily. We are not expecting much non-orthogonality since the mesh is going to be made with block mesh, so the correctors are set to 0. And we also have a provision for calculating our potential flow if we want to do that, since we've also included the phi field variable here. So essentially what you would want to do, if you want to do, is first run the potential foam application. This would give you an initial estimate of what your velocity field is going to look like, and then your steady state solver, the simple foam so to speak, the incompressible fluid solver, is going to take that as its stepping and essentially start the solution from there. It helps with faster convergence, so on and so forth. You could do that if you would want to. And we've also created the relaxation factors for our velocity and turbulence parameters. Pretty standard stuff there. Okay, now that we have seen the individual files here, now let's go ahead and look at what our mesh could look like. So we have our terminal here. Now let's first make the mesh. Okay, so first thing I will see here is that the number of cells that I have, 625,000. This is quite high, but for the case at hand, this is required. So when I first run the block mesh utility here, you can see that it is first trying to calculate the different functions that are present there. So it's just gonna do this calculate 4 different times, or rather 5 different times. And once it is done doing all of the calculations, it's going to read the simple line here, or rather the line.vtk object. So once it is done reading that, it is going to extrude my circle that has been made across this entire line. At the same time, we have defined certain vertices so that we can control the mesh grading across our particular pipe as well. So the different blocks that we have created right here, we can see the sizes. At the same time, towards the end, we have defined our boundaries, the inlet, outlet, and walls. And this also gives us information about the bounding box. It also gives information about the number of cells that we have. So let's take a look at it in ParaView. So I've created the .foam file. I'll hit apply. So you can see this is our pipe. In the length dimension, it starts at -2, ends at 0. Then we have its bounds. The delta is very close to 2 centimeters, as you can see right there. Let me zoom in a bit and show you what the mesh looks like. So, yep. So this is what my mesh looks like, as you can see right here. In the middle, I've made a square this square is essentially there to help ensure that my mesh is made as properly as possible so that I don't have, skewed elements around. Now, the fun part about the mesh that we have made right here with the Reynolds number 10,000, velocity 0.5 meters per second, and the diameter of 2 centimeters is that the first cell layer height, it's supposed to be somewhere around 1 mm. So if I want to take a look at that, you will see this is somewhere around 1 mm, and this is exactly why I cannot make more cell layers closer to my pipe right here. Now, if I want to do that, it is of course possible. I can reduce the number of divisions in my circumferential as well as the radial direction. More likely the radial direction than the circumferential. But if I choose to do that, then that would reduce the cell resolution that I have, or rather reduce the cell count, and I'll not be able to capture the steep gradients of my parameters such as your velocity, pressure, etc. near to the wall. So this is what I've chosen to do. The cell grading or the mesh grading of 40 essentially ends up giving me this type of mesh. You can play around with it and help make this mesh a little better. As you can see, closest to this square, this length right here, this is somewhere around 2e minus 5. So let's take a look at what the solution will also look like. Okay, so as you can see, we've run it for 20,000 iterations. For the 20,000 iterations, this is my inlet, or rather, if you just want to isolate the inlet, and I want to do this. So yeah, this is what the pressure across my particular inlet of the pipe is looking like. So let's do one thing. Let's create a line from the center of this pipe and have it run all the way to the outlet right there. Now we will remove the velocity magnitude, we'll remove K, nu T, omega, and the y plus, right? Okay. So somewhere around the inlet, the value is closer to 0.382, as you can see right there. And of course, since the outlet is set at 0 in our boundary conditions, the pressure drop that we expect is somewhere around 0.382, which we, if then multiply by our density, if you want to do that, we could just simply call it static pressure, or let's call it static. So here I will do pressure times density 1000 for our water and hit apply. So this is the P static that we have. There we go. So the maximum value is of course to be expected at the inlet, 382.7, somewhere around there. Now the theoretical value that we wanted to calculate was somewhere around 386. So we're pretty close. So we know that whatever mesh that we have made, or whatever numerical schemes that we have used, actually work in predicting what our pressure drop could be for this particular case. Now of course we could do multiple things here if you wanna change it up a little bit. So one of the first things that I would like to do is take a look at how my pressure changes, or how my velocity rather changes in the radial direction across the different lengths. So to do that, So the mistake that we've been making is we're giving the positive values. We need to give the negative values. So we can see how the velocity values change. Let's change the, legend. And similarly, let's make one last line somewhere around the exit. So you can see at the different lengths what exactly my velocity value is looking like. The shape is much more parabolic. Towards the end it has fully developed sort of. And if you see this variation, as you keep going towards the 0.5 meters, 1.5 meters, so on and so forth, you will see the flow trying to develop itself. I would leave that as an exercise for the viewer here. You can check out the case setup files right down in the description in our GitHub link. If you have any questions, please let me know. So there you have it. We've successfully built an OpenFOAM simulation from scratch and validated it against fundamental engineering theory, achieving an error of less than 3%. This process is the foundation of all professional CFD work, but what happens when the geometry isn't a simple straight pipe? For instance, what would happen if we add a bend? In the next video, we will level up our meshing skills using Snappy Hex Mesh to tackle this 90-degree bend and validate it using the minor loss coefficient. Thanks for watching. See you in the next one.